First set in our book is, or first lesson is from the R.1 section out of your textbook, and that's R for review, and we're talking about sets. Okay, so not a whole lot of mathematics in this one as far as add, subtract, multiply, divide things, but we're going to talk about sets. And a set of things is a set, like a set of golf clubs. It's a collection of objects. Okay. In a math class, that's usually numbers of some sort. You know, certain kinds of numbers we can put in a set. Inside of that set, there are things called elements. It's a piece inside of a set. A lot of definitions in this first section. Sorry, just is the way it is. Okay, a piece inside of a set. Okay, if something is inside of a set, we can use a symbol called epsilon. And the way to make an epsilon, it's a Greek letter. Make a C, like a lowercase c, and then put a little dash in the middle of it. That's the Greek letter epsilon. Okay, and I'll show you that what that looks like in just a second, how we're going to use that. Okay, set is a collection of objects. Elements are the pieces inside of that set. And the way we write a set is with set braces. Set braces look like this. Yours don't have to be perfect, but don't do this, because that just makes me think, oh, I'm going to make a butterfly out of that. That's what it looks like. Try to make the little curly braces. It's what I call them. I call them curly braces most of the time. But the set braces are what they're called in a math class. Set braces, try to draw them neatly. Most of the stuff you're going to do is going to be online or on already written for you anyway. So, but when we do the labs, try to draw them decently. Here's an example of a set. We'll call this set S. Set S. So numbers 1, 2, 5, and 7. No real rhyme or reason to picking those numbers. I just picked 4 numbers for use. Okay. Each of those numbers inside are elements of that set. So the way that you would say that is you could say 2 is an element of S. That's the math notation. 2 is an element of S. That's how that's read. Okay. 2 epsilon S means 2 is an element of S. That's the way we write that. And the converse to that, 3 is not an element of S. So I write it the same way. I use the same letter and symbol, but then I put a slash through it. It says it's not an element of it. 3 is not an element of S because 3 is not in it. Okay? So that's how you would write that. 3 is not an element of S. That's how you would read that when you get that. Okay? So 2 is an element of S, is 2 epsilon S. 3 is not an element of S, means just put a slash through the epsilon symbol there. Okay? Now, there are different kinds of sets. One of those kinds of sets is a finite set. Does anybody know what the word finite means? There you go. A finite has a start and a finish. It's a limited number. One kind of a shorthand way of remembering that, a finite set, you can count stuff in it. You would be able to count it if it's a finite set. Okay. Well, what's the opposite of finite? Infinite. Yeah. An infinite set, it's unending, because that's what infinity is. Unending, unlimited number of elements. Example of a infinite set would be something like all the multiples of 3. That's an unlimited set because you could always find the next one by just multiplying the next number by 3. Okay, that would be an infinite set. A finite set would be something like the natural numbers between 0 and 10. There's only certain, between 0 and 10 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the only natural numbers between. There's a finite set out of that. Infinite set, never ending. Finite set, it's got a, Cindy said it's start and finish. We can count how many pieces are in it. It's a finite set. Okay. All right. Let's look at the natural numbers. Natural numbers. The natural numbers are the numbers that you count with. So when you started counting in elementary school or preschool, the first number you started with was what number? 1, right? Put stuff on the table and tell my 3-year-old to count them. He starts with the number 1. That's natural. That's why they're called the natural numbers. The natural numbers are 1, 2, 3, all the counting numbers, all the way up, okay, to infinity. The natural numbers, the way that we denote the natural numbers is a capital N, but instead of just doing a, like this, double the bar in the middle. Double that bar in the middle, and that's the abbreviation for natural numbers. So we don't have to write natural numbers over and over and over and over because we use it a lot in this first little chapter that we're doing here. Okay, the natural numbers, and those natural numbers are, you start 1, 2, 3, 4, 5, and then dot, 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 dot. Now, are the natural numbers a finite or an infinite set? Yeah, they keep going. When we think we've gotten to the end, just add 1. You got the next one. Add 1. You got the next one. They just keep going on forever. So the natural numbers is a good example of an infinite set. That's an infinite set. Just, I guess we'll call that common knowledge from here on out, because we know that the natural numbers, we could keep counting for a long time. Okay, so natural numbers 1 through forever. Okay, now another type of set that we could be looking at might be this set: 1, 1/2, 1/4, 1/8. What's the pattern that's going on here? Do we see a pattern in those numbers? Yeah, I'm splitting it in half every time. Half of 1 is half. Half of a half, I take a candy bar and I break it in half, and then I take those halves and break them in half, I got fourths. If I take those fourths and break them in half, I got eighths. The next number in this list would be what? And then 32nd, 64th, and keep going. So that's the pattern that's going on. But the dot, 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 dot at the end tells us that this set is what? Okay, so there's a notation thing for infinite. If you see the dot, dot, dot at the end, oh, that's got to be infinite. They're going to keep going forever with that. Okay, that same pattern, but recognizing patterns and seeing that these are not a special type of number. They're just fractions, but it's an infinite set. That's what we're going for here. Is that infinite or finite? It's infinite. Here is another set. 7, 8, 9, ... 15. Huh. What's the pattern going on in this one? Yeah, they're just getting the numbers from 7, 8, 9, blah, 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 and up to 15. The ... in the middle is all the stuff in the middle that they're just not wanting to write because it's the same pattern over and over. But the 15 tells us that it's a finite set because it's got an ending spot. It's got a starting spot and an ending spot. So this is a finite set. So there's some examples of infinite and finite. Okay. Here's another way that they might write a set. This is more of a math, an algebra class type style writing a set. In high school, we call this set builder notation. But the idea here is this finite or infinite? Well, here's how you read it. All this means is that this X out here in the front, that's the one that's kind of confusing sometimes. All it means is the variable we're looking at is X. It doesn't really mean anything about what X is. Stuff tells you everything that X is. It's the way you read this mathematically is you say this is X such that 9 is less than or equal to X is less than or equal to 13. So let's go back to that basic definition of finite. Does it have a starting spot and an ending spot? Yes. So this would be a finite set. So if you can get that idea of finite has starting and ending, we can find all the pieces in between, count them up. That's the idea. All right. Now let's look at a little exercise where we're supposed to list the elements for each set. Okay, that's the instructions that they give us. We're going to call this example A. I tend to letter my examples instead of number them for no apparent reason, because I've done it that way I've been teaching for 12 years. I've been doing it that way since I started. I don't know why I started that way, but that's what I've done. So now what I'm going to do is I'm going to write a set, but it's not going to have all the numbers in it. I want you to write all the numbers that would be in that set. So here's our set, X such that X is a natural number less than 7. Okay? So we're going to write that as a list of elements. What are elements again? They're the pieces inside. Okay? They described them in their definition of the set. We want to actually write them there. All right? What are the natural numbers that are less than 7? Why not 7? That's exactly right. It said less than, so we can include 7. If it had said less than or equal to, then 7's included. So here's a finite set, and we've listed the elements in there. Okay? It probably won't have that as an option. It wouldn't be wrong technically, but most of the time it's going to get most of your Canvas stuff. It's going to have pick the correct answer. It's like multiple choice kind of type stuff. I do that because the ones where you type them in, if you don't type it exactly like it, I try to avoid those kind of questions because of the trouble. if you type it in using an X and they expected it to be a Z, then yeah, and that's one of the reasons I try not to use it, just because I don't like the syntax that you got to do. Yeah, very, very. Yeah. It's a fence. It's a computer. It doesn't know. All right. Here's another set. X is a natural number greater than 7 and less than 14. X is a natural number greater than 7 and less than 14. Again, we're just listing the elements that are in that set. What's the first natural number that's greater than 7? And it goes 9, 10, 11. Well, yeah, you could do ... and end at 13. Yeah, that would be also an option. 8, 9, ... 13. That would also be an acceptable way of that being the correct answer, because it shows the pattern and then gets you the ending point. That's the idea. Okay. So an easy thing. A lot of the problems you're going to see where you have to write the elements are talking about the natural numbers, and that's why we kind of went over what the natural numbers were in this section. We'll do some more stuff with all the different kinds of numbers in just a little bit. But all right, a few more definitions to get here, and then we'll get to some more examples. So universal set. Now, these and R's look alike tonight. Universal. UNIVERSAL. My B's and R's really do look alike. I didn't know that. A universal set. Anytime it talks about a universal set for a problem, it's talking about everything in the discussion. Okay? A universal set usually is like they will give you, like if you've got a problem and they give you 4 or 5 sets and they'll say, well, this one is the universal set. It'll say, hey, for this problem, universal set is this one. And then you'll know, okay, I'm building everything off of that. The universal set is the big picture. Okay, that's what we're getting everything off of. The null set, N-U-L-L, null set. Fancy word for the empty set. It has no elements. The notation for that is either just empty curly braces or a circle with a slash through it. Both of those mean the null set or the empty set. It has nothing in it at all. Okay? The null set, the empty set. Okay? One more definition. Subset. A subset, a smaller group of elements from a larger set. Subset. Seems intuitive. Bigger set, you take some of them, you make a subset with it. Okay? All right. Let's look at an example. Example C. A. Set A is this one. 1, 2, 3, 4, 5, 6, 7, 8. And I'm just listing them all because it's pretty small sets. Anyway, Set B, 2, 5, and 7. Okay. Here's the question. Is B a subset of A? Are all the elements in B part of A? Yes. So the answer to that would be yes. Now here's some notation. B is a subset of A. That's the symbol for subset. It's like a capital C with a line under it. The way you read that is B is a subset of A. That's the way that's read. B is a subset of A. Example D. Same set A. I'm going to call it set C. All right, let's use set D instead of C because the symbols. 10, 15, 8. Is D I can write it with symbols since we talked about that, notation-wise. It says, is D a subset of A? No. D is not a subset of A. So anytime you want to write that with notation, to make something not, you just put a slash through it. Really easy, simple thing for mathematicians to do. Okay. All right. You may know what that's called. Remember the name of those? Yeah, it's been years since you've seen one of those. Venn diagrams. Venn diagrams are very handy for dealing with sets and in overlapping sets and that sort of thing. Okay. We'll let this be example E. I'm going to put this left circle, we'll make it blue. And that's going to be set A. And then set B is the black one. Okay. I'm just going to list the elements in A. 3, 5, 7, 9, 11, 13. I'm going to list the elements in B. And then we're going to put them in the Venn diagram. Okay. That's the practice I'm after here. 6, 8, 10, 11, 13, 14. Okay. There's the elements in A and the elements in B. Let's put them into the Venn diagram. Okay. The way Venn diagrams work, what goes in the football shape in the middle? The shared pieces. That's right. So anything that's shared goes in the overlap area. So what's shared for these two sets? 11 and 13. So those should be the only numbers that are in the football shaped area. Okay. What numbers are only in A? 3, 5, 7, 9. And then we got 11 and 13 are also in A. So everything that's in the blue circle is in A. Now what goes in the black circle? We've already got 11 and 13, so what else goes there? 6, 8, 10. Yeah. Where do they go in the football area or the other area? The other. Okay, so we've got to make sure we put them in the right spot. So 6, 8, 10, and 14. So now we filled out the Venn diagram correctly. Okay, we've got everything done there. Now, within that, we can do this notation deal. A intersect B. That's the symbol for intersect or intersection. That's a set. The set of elements that are in that intersection are the things that are in A and B. Okay? A and B would be 11 and 13. Okay? An intersection is an and. Okay? Intersections are ands. Unions are ors. What are the elements that are in A or B? Doesn't have to be in both. Just got to be in one of them or the other one. Well, that's all of those. 3, 5, 7, 9, 6, 8, 10, 11, 13, 14. A union is an or. Unions have a lot more stuff in them than intersections do. Okay? And this is probably because sports guy, name me somebody that's good, that is a professional football player and a professional baseball player. Bo Jackson was. That's one. Deion Sanders, that's 2. Yeah, he's got a contract. Never played a major league game yet, but that's coming. Tebow hasn't played a major league game yet, but that's coming. We don't get hurt again. Let's see, Brian Jordan played for the Cardinals and the Braves. He was also played for the. But that's a small number. That's 5 people. How many people play in the NFL? A lot more than 5, right? How many people play in Major League Baseball? A whole lot more than that, right? So the and, to be good at football and baseball, is a really exclusive club. An section is an exclusive club. A union, not so exclusive when we're talking about sets. Because if we're talking about the union of professional football, professional baseball, that's a lot of people. But the intersection of the ones that play both is a very small set. We had to go back to the 80s to get Bo Jackson there before he got hurt. All that stuff. So it's a small number. It's smaller now than it ever has been, but it has always been a small number and will always be a small number. Okay, so unions, that's in this one or that one. Intersections, it's got to be in both of them. So the intersection is a smaller set. Okay, intersection should be a smaller set. Let's look at some sets that may not be written into a Venn diagram. Say we had set W, 9, 15, 25, 36. Set X, 15, 20, 25, 30, 35. Question number 1. Write the at the intersection of those two. What's in the intersection? 25 is the only number, and 15. We got 15 and 25, both numbers. 15 and 25, small set. What about the union of those two sets? It's all of them, right? 9, 15, 20, 25, 30, 35, 36. Everybody in the pool. That's it. A union. Do a short one here. Set G, 1, 3, 5. Set H, 2, 4, 6. G intersect H. What's in that set? Nothing. So it's the what? Yeah, the null or empty set. So you could write it this way, or you could do a circle with a slash through it. Either of those is acceptable because there's nothing that's in both of those. No intersection of those. All right. Let's look. One more definition for this section, and that's the complement. Not compliment like I like your shirt, but complement with an E of a set. All right. A complement of a set are pieces or elements that do not belong to a set. That's normally from a larger or a universal set. Okay, so the complement of a set is something that's not in the particular set we're talking about. Okay, let's look at an example here. Example H. Let A 1, 2, 3, 4, 5, 6, 7. A is the universal set. I'm declaring that. I'm telling you that. Okay, that's the universal set. Nothing else. Okay. Set B 1, 3, 5, 7. Set C 3, 4, 6. All right. We're going to answer several questions that kind of tie everything we talked about with sets in this particular section together, and then tie in the complement idea with it as well. Okay. So, question number 1: is B a subset of A? Is everything that's in B in A? Yes. So it has to be a subset. Question number 2: is C a subset of A? Yeah, it is too. All right. Here's where we throw in the new thing. Okay. B, and the way you say that is B prime. It's just an apostrophe kind of there, like a little apostrophe right there. That B prime, that's how you read it. What that means is the complement of B. Okay, so the complement of B are what elements from the universal set? And remember, a complement means the pieces from the larger set that are not in the given set. So B prime, what are the elements that are in B? 1, 3, 5, and 7, right? Okay. Which elements in A are not in B? 2, 4, and 6. That's what a complement is. In the universal set that's not in the set that we're asking about. That's exactly what it is. Okay, it's the pieces that are in the universal set that are not in the set they're asking about. Okay, that's what a complement is. Okay, let's do the same thing for C prime. What's the complement of C? C has 3, 4, and 6 in it. And 6 is in C, so 6 can't be part of the complement, so it'd just be 1, 2, 5, and 7 out of that. That's what a complement is. Pretty simple idea there. All right. So some things with sets. We're not departing away from sets completely for the next section, but just some basic set information there. We're going to deal with more specific number sets in section 2. All right. All right. So let's look at section 2. R.2. Real numbers. Getting a little closer to doing some math and their properties. There's a guy that works on computers at our high school. He's from Slovakia. He's been in the U.S. for a long time, but he still has a pretty thick accent. I always like how he says properties. He goes properties. That's how he says it, and that's how I always hear it when I say it. I'm like, man, I don't want an accent, but if I had one, I think I'd pick his. It's just the way he says things are funny. But he's a great guy, really good at computers. All right, now real numbers. When we're talking about the real number system, there's kind of this. Have you ever heard of Russian nesting dolls? You know, where it's got a big one and then you got smaller ones inside of that. The number system works kind of like that. Okay, it's like you got this big box. So draw yourself a big old box, and inside this real big box is the complex number system. The complex number system is bigger than the real number system. Okay? Complex numbers, examples of those are things like 2i, negative I, 3i, negative 5i, things like that. The I comes from the square root of negative 1 is where that comes from. If you don't remember that from some sort of algebra class you've had in the past. Inside of this box is a slightly smaller box, but still pretty good size. It's the real number system. Okay? The real number system has several boxes inside of it. Okay? Inside of the real number system, you got a pretty big box. It's the rational numbers. Okay. Rational numbers are numbers that can be written as fractions. Okay. So 3/4, -7/9. Examples of those. Okay. This little sliver right here, that's the irrationals. I've drawn a small box for that, but there's a lot of them. Okay. Square root of 3 is a good example of that. It's a decimal number that doesn't repeat and never ends. If you take the square root of 3 with your calculator, it'll give you all these digits. If you go with your smartphone and you do the calculator and you turn it sideways, and it'll give you a lot more digits. It'll keep going. It keeps going forever. Okay. A irrational number is a number that cannot be written as a fraction, and it doesn't repeat and doesn't terminate as a decimal. Square root of 3, square root of any prime number is an irrational number, and there's an infinite number of prime numbers in the world. One of the professors at the main campus, I don't know if anybody's taking classes there at the main campus, Dr. Chris Caldwell was his name. One of my favorite teachers there. He's a big prime numbers guy, and like he's on the committee for the world where they're trying to find the next largest prime, and there's like a monetary prize for finding the next one. And he's one of the guys that gets to review it and make sure it's a prime number. It's pretty impressive. But any square root of a prime number is an irrational number. So the rational numbers, that's a pretty big box. It's got a lot of stuff in it. The irrational numbers, it's got a lot of stuff in it. Okay? The reason this box is smaller is because we're not dealing with irrational numbers a whole lot right now in this course. We'll get to them, but not right now. We're dealing more in this red box here. Okay? So the rational numbers, inside of those, well, there's integers. Integers. What the heck's an integer? Well, it's a positive or negative whole number, right? So like -4 is an integer. 6 is an integer. Okay? So I'm going to put -4, -162. Inside of that box, though, there's another box. It's the whole numbers. The whole numbers are, well, the whole numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. Inside of the whole numbers, one last box, and that's the natural numbers. Remember we had that abbreviation for natural? Is that N with the double bar in the middle? That's the natural numbers. The natural numbers are the count numbers starting with 1. So here's the way it works. If I pick a number and it's a natural number, it's in this box. But guess what? It's also in the whole number box. And guess what? It's also in the integer box. Guess what? It's also in the rational number box. Guess what? It's also in the real numbers box. Okay? Well, if I pick a natural number like 7, 7 is a natural number, a whole number, an integer, and a rational number. It's also a real number, but we already knew that. Okay? So if I pick something, an integer like -6, -6 is an integer, but it's not a whole number because it's negative. It's not a natural number because it's negative. So it's an integer, but it's also a rational number. Okay? And it's also a real number. Okay? Because it's in those boxes. If I pick the number 0, 0 is a whole number, but it's also an integer. It's also a rational number. It's a real number. Okay? So when we pick something inside of an inside box, it's also part of the other boxes too. Okay? So if you put something inside of that smallest Russian nesting doll, you put something inside of there, and then stack it all back together, let's inside all of them in it. Same way with these boxes. If it's a natural number, then it's got to fit all of them, okay? So what we're going to do is we're going to take a set of numbers, and then we're going to list which ones are natural, whole, integers, rational, irrational out of that, okay? And hopefully this will help us understand the number system a little bit. So here's our set. -8, -6, -12/4, -3/4, 0, 3/8, 1/2, 1, the square root of 2, the square root of 5, 6. Just some randomly selected numbers. Now, we're going to list the sets. So this is like our universal set. We're going to list the subsets that meet these criteria. The natural numbers. Okay? And remember, the abbreviation for that is the N with a double bar. I'm going to show you abbreviation for some of the others as we go through here so that you've seen those before. All right. Natural numbers means the counting numbers that are bigger than 0. Which ones are those? 1 and 6 is the only ones. Okay. The whole numbers, the abbreviation for whole numbers is make a W and then double the bar on the first one. That's the abbreviation for whole numbers. It's like that. What does the whole numbers add to the natural numbers? The 0. That's it. 0, 1, 6. So kind of thinking out loud here, this is not something we're going to write down, but are the natural numbers a subset of the whole numbers? Yes. That's the way it works. In this universal set and in the big picture of all the numbers in the world, the natural numbers are a subset of the whole numbers. And the whole numbers are a subset of which set? According to our boxes here. Whole numbers would be a subset of the integers. And the integers would be a subset of the rational numbers. And the rational numbers are a subset of the real numbers. That's how that kind of works there. So let's look at another set. Let's do that. Let's do the integers. All right, this one's going to blow your mind because it's not an I. You'd think it would be, but it's not. It's a Z. And you double the bar. I don't know why. I couldn't tell you. Some smart Greek guy came up with that. I think I had some other meaning, so they couldn't use it. It was taken. Okay. So integers. What are the integers in our universal set there? Almost all of them, but not all of them. So we got -8. That's an integer. -6. That's an integer. Okay. Okay. So what about -12/4? It's a fraction, but what is -12/4? So is that an integer? Yes. It's just not written like one there, but it does end up being one. So that would be an integer, even though it's not written that way in the original set. What else? Zero's an integer, 1's an integer, and 6 is an integer. All right, this is going to blow your mind too. The rational numbers, it's a Q. And you just kind of put a little slash there in the side of the circle part of the Q. That's a rational number. I know why that one is. Q stands for quotient, and a rational number is a fraction, and fractions are just division, so it's a quotient. That's what rational numbers. That's where that's coming from. So rational numbers, remember, they're the numbers that can be written as fractions. So we got -8, that could be written as a fraction, just put it over 1. -6 could be written as a fraction, just put it over 1. -12/4, that's a fraction. -3/4, that's a fraction. 0, I can put it over 1, that's a fraction. 3/8, that's a fraction. 1/2, that's a fraction. 1 over 1. And then 6 over 1. I could write all those. Here's a neat way of writing that. What does that mean? Q prime. So it's the complement of the rational numbers, which are the irrational numbers. What in our universal set are not in the rational numbers? There are only 2 of them. Yes. So we get that set practice with the notation and all that, and hopefully get a little understanding about how that number system kind of builds itself there. But it's just writing some sets, and if you'll keep that idea of that each box is inside of the bigger box, that'll help you kind of understand some of that set material when you're talking about the number types. Okay. All right, let's do some math. Let's get to some numbers and actually doing some math. So for whatever reason, they put this in the same section. It's a review section, so it's kind of like hodgepodge of this and that. Nothing really incredible. Let's write this down first. I think everybody knows this, but I always try to remember to write it down. Order of operations. What should always happen first when we're doing a math problem? Parentheses, or any kind of grouping symbol, like absolute value symbols are also considered parentheses. So anything happening inside of those. Brackets, like square brackets, are considered parentheses. Any kind of grouping symbol is what it means. Parentheses, and then what? Exponents. So if you see any exponents in the problem, you're going to work those next. And then after that, the M is for multiplying. And the D, divide, division. Be careful there on that. It's not always multiplication first and then division. It's multiplication and division left to right. So if division happens like the first thing you come to, left to right, then it's going to happen before the multiplication does. Multiplication and division are same level. They're ranked the same. They're both lieutenants or something. And so it's whichever one you come to first is the one you do, left to right, okay? The A is addition and subtract. Same idea with the addition and subtraction. They're going to happen after multiplication and division, but addition and subtraction should happen left to right, okay, as far as doing that out of that, all right? Let's do a little bit of exponent work here just so we remember how exponents work. That's something we sometimes forget. Exponents, when you're dealing with exponents, a to the n, this part is called the base, the a. The n is the exponent. A good example would be like 4 to the third power. 4 is the base. 3 is the exponent. That's what we're dealing with there. What does 4 to the third power even mean? Yeah, it means 4 times 4 times 4, which happens to be 64. Not that you have to have that memorized. You can use a calculator to help you. If you need to do an exponent with the calculator, I'm going to show you with the graphing calculator how to do that. So to do 4 to the third, I'm on the regular calculator screen. I hit the base 4, and then to get an exponent, right here underneath the clear button is this little caret symbol. Looks like a little house top. That's what it looks like. It's called the caret symbol, and it just makes X, and you need to put the exponent in there. 64. And hit enter and it tells you. Okay? Or you could write out 4 times 4 times 4. Same thing. Okay? Any way you want to do that. You don't have to have your numbers cubed memorized. It's just not high school math. I don't have time for that. Okay? So anyway, example C, -6 squared. Those parentheses are important. So don't write them down. You got to have them. What does that mean you're squaring? You're squaring -6, not just 6. Okay, so it's -6 times -6, which turns into +36. The difference comes in here when you have something like this, negative, and then 4 to the fourth. We'll do something like that. The parentheses is important here, because order of operations, the way it works is it says, okay, parentheses, well, there aren't any in that problem. So where the next thing you go to are exponents. The exponent is on the 4, not on -4, but on 4. So you do 4 to the fourth power. The negative that's hanging out in the front, the order of operations way of looking at that is like they're saying -1 times that. That's what that means. The negative happens last in that problem. So 4 to the fourth power is 256, and then -256. Now again, I have those memorized because I've done them a million times. Okay? You don't have to do it. 4 to the fourth. If you're typing it in the calculator, the parentheses really do matter. So if you're using the graphing calculator, and if I type in -4 raised to the fourth, it's going to do what I intended. If I do this, big difference in -$256 and +$256. You don't believe me? Ask your bank. I mean, that's the big difference there. All right, so be careful about parentheses and when you're typing things in your calculator. The graphing calculators are very sensitive to order of operations. They do exactly what you type in. If you don't type it in the way it should be typed in, it's going to be wrong. Okay, so you're meaning to raise a negative number to an exponent, put it in parentheses. If you're just taking a number, raising it to an exponent, and then making it negative, you don't need parentheses. There's a difference, big difference. Okay. All right. Let's look at example E, an actual order of operations problem. 4 times 3 in parentheses squared plus 6 times 4. Okay. So with the graphing calculators, one of the nice things about those is that you could just actually just type that problem right into it, exactly like it's written. I could do parentheses 4 times 3, close parentheses, squared, plus 6 times 4. 168. It does the order of operations for you automatically. You don't have to think. Okay? But you're a button pusher. And usually button pushers gonna have some problems when we start throwing some letters in there. Okay? So let's think a little bit about what the calculator is actually doing. Okay? It's following the rules. the rules tell us what should happen first with this problem. Parentheses. There's parentheses here. 4 times 3. That's inside of there. I'm going to work that first. 4 times 3 is 12. So the first step is to get 12 there. I'm going one step at a time here. I'm not trying to get too crazy. The next thing to do after we've taken care of the work that's inside of the parentheses is to do what? Exponents. Well, the exponent's on the 12. It's 12 squared. 144. So that's 144. And then the next step is multiplication, division, left to right. Well, there's no multiplication here. That's addition. That's not next. 6 times 4. There's a multiplication to do. 6 times 4 is 24. We have 144 plus 24, 168. Same answer, but knowing that is going to help you when you start doing things with letters in there. Because you can't just type the letter stuff in the calculator. You got to be able to do the order of operations with the number part and then put the letter part together. Okay, so be diligent to try to get things done right. So let's look at this one. 6 divided by 3 plus 2 cubed times 5. You'll rarely see me use a division symbol like that. After tonight, you probably will never see me use a division symbol like that, other than maybe the labs that we do next week or the next time. Okay? Parentheses are none. So next step, exponents. Okay, so there's an exponent. I see one of those. So 6 divided by 3 plus 2 cubed. 2 times 2 times 2. 8 times 5. Okay? After exponents are multiplication and division left to right. Which one happens first? Division on this one because it's first. It's left to right. 6 divided by 3. 2. Can I go ahead and do the multiplication of 8 to 5? They're the same level, right? Remember, multiplication, division, both lieutenants, they're at the same ranking, so we can do them together. So we do left to right. 6 divided by 3 is 2. 8 times 5 is 40, and we add them together and get 42. Graphing calculator, you can check yourself. 6 divided by 3 plus 2 raised to the third times 5. 42, same answer. Okay. Don't jump to the calculator automatically, even though it's nice. Think a little bit. It's going to help you. I tell my Algebra 1 students that I have right now, they're freshmen in high school, so they know a lot more than I do, how they are. I tell them, try not grabbing your calculator today. Try to do as much as you can without it until you absolutely have to have it. You will get better at that. The less you use your calculator, the more your brain will work, and your brain's way smarter than any calculator that ever existed. I mean, it can do so much more, so much faster. But you got to train it to do it. The only way to train it to do it is to make it do it. Okay? All right. 4 plus 3 squared. All of that over 6 minus 5 times 3. So you got this big fraction looking deal. So this one's a little tougher to just straight type into the calculator. So it's always helpful to just be able to work kind of the top part and then work the bottom part and then deal with the fraction part after that. So let's just work the top part. Let's do order of operation on the top. Parentheses, there are none. There's an exponent. So 4 plus how much? 4 plus 9 on top. So that would be 13, right? Well, let's do order of operations on the bottom. 6 minus 5 times 3. What should happen first? Multiplication. 5 times 3 is 15. So 6 minus 15. Ooh, maybe that's a little tough for you. That's correct. -9. If you're having trouble with that, just that's okay. Sometimes those negatives give us trouble. Okay, that works. And now, last step is that division. And does 9 go into 13 evenly? No. I just leave it as that improper fraction like that. I wouldn't even do anything else. Because it doesn't go evenly, it's not going to reduce any. Just leave it that fraction. Makes it work out real nice. Now, if you wanted to type this into the calculator, the TI-84, and this is another reason that I'm a big fan of it over the 83, is to take that calculator, you can hit the alpha button and then y equals, and it comes up with this little menu, and it'll make you a fraction, and you could type it in, 4 plus 3 raised to the second. And then you go down to the bottom part and you get 6 minus 5 times 3. The 83 will not do it like that. It can't handle that. It doesn't have enough memory or processor to be able to do that. So there's a nicety, again, of the 84 over the 83. So, and there it is, that -13 over 9 that we found. This negative out in the front is the same thing as if it were on the 9. And those are equal. All right. Nice things. Nice things. All right. Next thing in the evaluating. If I ask you to evaluate something, what am I asking you to do? Check it out. Work it out. Get the answer. You mean some sort of so we're going to evaluate when x equals -2, y equals 5, and z equals -3. So we're going to deal with some variable expressions. Got the letters in there now. Got it? -4x squared minus 7y plus 4z. That's our expression that we're going to evaluate using these variables. So all I'm going to do is take those numbers, plug them in the place of those letters. We have -4. And I always, when I plug them in, I put them in parentheses. That usually helps me remember to put the sign with them and stuff like that. So -2 squared minus 7 times 5 plus 4 times -3. Next step, just work it out. -2 squared is 4. So we've got -4 times 4. I already know 7 times 5 is 35. And 4 times -3 be -12. So I just got to work out that last little multiplication thing, so -16. That'd be -51 minus 12 be -63. Wonderful. With the calculator, you can just type it in just like that plug-in step. Minus 7, 5 in parentheses, plus 4 parentheses, -3. -63. Really nice with the graphic calculator. Be able to just type it in and make it look just like what you're writing, and check your work. Again, if you'll work your way up to try to do as much as you can without the calculator, it'll be great. It'll help you out later on. It'll make your brain stronger. Kind of like lifting weights. I don't know. You square -2, get a positive 4. Times -4 is -16. 7 times 5 is 35, we're subtracting. Okay, 4 times -3 is -12. And then when I put all those together, -16 minus 35 is going to be -51. And then I'm adding -12 to make it plus a negative. There you go. That'll get it. Those sign mistakes are the most common ones. All right, look at this one. 2 parentheses x minus 5 squared plus 4y. All of that over z plus 4. Well, this one's a little tougher. I used to go here. Again, we're using the same x, y, and z values on this one. So x is -2, y is 5, and z is -3. So we're just plugging those in. -2 minus 5 squared plus 4 times 5 over -3 plus 4. And if I take it step by step with order of operations, -7. Go ahead and multiply those. Go ahead and add those so I can work the bottom. 2 times 49 plus 20. 2 times 50 is 100, so minus 2, so it would be 98 plus 20. 118. Technically, it's over 1, but I don't have to write that because divided by 1, it's the same. And again, with the graphing calculator, with the 84, you can get that fraction thing by alpha and then the y equals button, and then just straight up, type it in just like you would 2 parentheses and then parentheses -2 minus 5 close parentheses squared plus 4 parentheses 5. Down to the bottom, you got -3 plus 4. And enter. Nice stuff with the calculator. Help check your work, hopefully. All right. Okay, so that's evaluating expressions. Next thing that's kind of in the same section, it's also pretty simple, is the simplifying of expressions. So it looks a lot like the same kind of problem, but you're not given values for your variables. What we're doing here is we're looking for like terms. Remember that word from an algebra class in the past? Like terms is what we're looking for. So we're going to simplify an expression by putting the like terms together. What letter we're on here? J. Okay. 6 plus 9 plus x. 6 plus 9 plus x. What are the like terms in this particular problem? Because I know this is really a simple problem, but just get the idea started. They're both plain numbers, so you put them together. 6 plus 9, 15. The plus x didn't have anybody like him. Does that mean he's left out of the problem? No, it means he comes with us. All right? Leave nobody out. 15 plus x. If you wrote x plus 15, it's the same thing. You could have some issues. Might be something like this. Maybe you've got 3x minus 2 plus 5x minus 6. A little tougher problem, just more stuff. I just usually start with the first piece and say, oh, is there anybody like 3x? So it's 3x plus 5x, which would be 8x. Putting the like stuff together. And then, so I've used those two up, and then I go to the next piece. -2, is there anything like a -2? That's -6 there. They're both numbers. So what's -2 minus 6? -8. And we've simplified. We're good. Okay. Pretty simple idea. One more here. Let's do 3 parentheses 2x minus 4 plus 5x plus 10. Kind of step it up a bit. Anybody remember what property this is? I remember how to do it, but I don't remember the name. Yeah, distributed property, that's what it's called. And what that means is you're going to take this 3 and you're going to distribute it to everything in the parentheses. You're going to multiply 3 times 2x and 3 times 4 and get those pieces. Okay, so order of operations still in play here. Forever, order of operations is the rules we have to play by in math. Okay, so multiplication's got to happen before that addition and subtraction of like terms. So I'm going to distribute this 3, get 6x minus 12. Good. And then minus 2, because -12 plus 10 is minus 2. Again, when you're doing just regular numbers, try to start training your brain and doing less and less with the calculator there, because when you start throwing the numbers in and the letters together, you can get done a lot faster if you're used to not doing it with your calculator. Okay. All right. So that's section 2. Let's go to the next section, R3. Polynomials, just a little bit of polynomials. We're not really going to do much with them other than maybe add and subtract them and name them some stuff with them. So first thing we're going to review are the rules for exponents. Rules for exponents. Okay. If I multiply a base that are the same, I add exponents. Okay. So on the left side, I'm going to do the rule. On the right side, I'm going to do an actual example. Okay. So that'd be like x to the 3rd times x to the 5th. The bases are the same. If the bases are the same, then I can add the exponents. If this is an x and that's a y, I can't do that. But because they're both x's, I can add the exponents together. 3 plus 5 would be 8. What that is, that's called the product rule. It matters if you know the names rules. Just know how they work. Okay? It doesn't matter if you know the names. Just know how they work. So if I'm multiplying and the bases are the same, add the exponents. Okay. Next one, it's called the power rule. You take an exponential expression and you raise it to an exponent. The way that works is you multiply the exponents together. Example, x to the 4th to the 3rd power. Multiply 3 times 4. Those exponents multiply. So it's going to be x to the 12. So we got two things in the parentheses. More than one thing. It could be two things, it could be 14 things. But they're all multiplied together on the inside. That's what's going on here. And we have an exponent on the outside. It's just an extension of this rule, but it's like distributive property is what the way it works. This P on the outside multiplies to each of those on the inside. Okay? Notice that the bases are different there. If they were the same base, then we would do something else. Example of that would be like x to the third times y to the fifth, all raised to the sixth power. Six times 3, 6 times 5. X to the 18th, y to the 30th. Simple rules. Just take some practice getting there. Okay. Here's another extension of the power rule. If you got a fraction in there, say we had a to the m or b to the n, and then some exponent on the outside. It's still the same rule as this one. It's like distributive property, but it goes to the top and the bottom. Just like this P went to both pieces here, it's going to go to both pieces here. Top and bottom. Okay? So that'd be A to the MP, B to the NP, like that. Okay? The example would be something like x to the 7th over y to the 3rd squared. X to the 14, y to the 6. Some basic examples is what I'm doing here. We got to the stuff yet. Some basic examples of those rules. All right, one more rule, and then we'll get to some real problems. Is the quotient rule. The quotient rule is the opposite of the product rule. So the product rule was if the bases were the same and you were multiplying, you did what with the exponents? So let's go back up to the top, the very first thing. What did we do when we multiplied? When we had the bases the same? We added. So if we're dividing, division is the opposite of multiplication, right? What's the opposite of addition? So we were doing a to the m minus n. It's always top minus bottom, no matter what. So if you had x to the 8th over x squared, 8 minus 2, positive 6. Okay, always top minus bottom. Bases have to be the same for that to happen. Bases have to be the same. All right, let's look at a few examples and see if we can apply these rules to some problems. I'm just going to start my lettering over because I don't remember what I was on. So A is where I'm starting again. Say the y to the 6th times y to the 5th. Are the bases the same? They're multiplying. What do we do with the exponents? It'd be y to the 11th. Good job. What if we throw a number in there? You got 3 x to the 3rd, and then times 4 x to the 5th. What do we do with this 3 in the front and this 4 in the front? What operation is going on between those two things? Multiplication. So we're just going to multiply. Nothing different about that. Just going to multiply those two numbers together and then do the exponent rules. So 3 times 4 is 12. And then we're multiplying. We got an x to the 3rd and an x to the fifth. So the bases are the same. Well, we can add them. So that'd be x to the eighth. Good job. We'll spin on this one. What operation is going on between all three of these things? Multiplication. Anytime there are parentheses around everything, it's multiplication. Okay? So, what can be multiplied together here?
6 and 9.
Okay? So the 6 and the 9 can be multiplied together. Can the 2 be multiplied times those? Does the number in front even matter as far as the y's and the x's? No. You can always multiply the numbers in front together. So we're going to multiply 6 times 9 and then times 2. Okay? The like terms have to have the same letter. Where that's coming from is if you're adding or subtracting. Multiplication, there's nothing stops you from multiplying. Okay? You can always multiply things together. Addition and subtraction has got to have the same letter. Okay? So 6 times 9 times 2 be 72 times, so 54 times 2 would be 108. And then now the letters, now there is some letter stuff to do. So you got x to the fifth and x to the third. That'd be x to the eighth. And then the y, yeah, nothing changes as far as y because there's not another y to put with it. So you just add it on, you know. Mixing in some different letters. X to the fifth squared. All right, so it'll be x to the 10. Good job. Eight x to the fourth cubed. All right, the x to the 12th is correct. What's the exponent on the 8 when nothing is written there? It's an understood 1. So what's the rule for this 3 to that 8 to the first? It's going to be 8 to the third. So we're going to cube that 8. I don't have that memorized. 512. Do now. That's our final answer right there. All right, so the 1, if there's not an exponent written on it, it's automatically a 1. Okay? And the product or the power rule says this exponent on the outside multiplies to every exponent on the inside, whether it's on a letter or a number. Doesn't matter. Okay, so 3 times 1 is 3, that's 8 to the third, and then the 3 times 4 is the x to the 12th. And then we just worked out what 8 to the third was. 5. Let's do this part. 0 exponent. 0 exponent. Anything to the 0 power is defined to be 1. Okay? So if you take my paycheck as a public school teacher, each year I make $3,846,784. I'll laugh because y'all know that's funny. I wish that was the way it was. That's what I'm worth. No, I'm just kidding. I'm not worth that much. I might be worth that much. But anyway, that big number to the 0 power, 1. That may be what I'm worth. Okay? Anything to the 0 power, if we take power t, we've been raising it to the 0 power quite a bit lately. 1. Okay? That's the worst power t I've ever drawn. It's okay. It doesn't matter what it is. If it's to the 0 power, it's 1. Okay? 0 power is 1. Know that. Okay? Anything to the 0 power is 1. All right. Let's get to polynomials. The whole name of the section was polynomials. We've been doing all this exponent stuff to get us there. So let's get to some polynomials and get something done with them. All right. So a polynomial. Poly means many. Okay. Terms added or subtracted. Okay. The terms, when I say a term, I'm talking about the pieces that are separated by plus or minus. That's a term. Okay. If it's separated by plus or minus, it's a term. Okay. Okay. If I say something about the coefficients, those are the numbers in front of the letters. The coefficients are the numbers in front of the letters. The degree of a term. The degree of the term is the sum of the exponents on the variables for that term. All right. When we look at a polynomial, we're going to get the degree of each term. The degree of the whole polynomial is the biggest one. Okay? The degree of the polynomial, degree of a polynomial is just the largest term degree. We're about to do an example and kind of start. It'll make sense. Okay? So we're going to find the degree of each individual term, and then when I ask for the degree of the polynomial, you just pick the biggest one. That's what you got to do. Okay? So let's look at a polynomial, and we want to state the degree of the polynomial. And that's our job for right now. Then we're going to build up some other stuff. No idea what letter we're on. F. So here's our polynomial. 2x squared plus 5x y to the third minus 6x. Something. And let's do plus 7. Just throw a plus 7 on there. Okay? Now, the first thing we want to look for before we find the degree is to look to see if there are any terms that can be put together. So to be a like term, you got to have the same letter and the same exponent or exponents on those letters. Okay. So when I look at this one, I got 2x squared. Is there anybody else that's got x squared? No. So there are no like terms for him or her. I'm not sure what a 2x squared is. 5x y to the third. Is there anybody that's like 5x y to the third? No like terms for that one. Anybody like a plain 6x? Nope. Any other plain numbers? No. So there are no like terms that I can put together. If there were like terms that I could put together, I need to go ahead and simplify them before I start doing the degree. Okay. So for this one, there are not any. So I'm going to go find the exponents on the variables for each term. This one has 4 terms, so I'm going to find 4 different degrees to find the one degree that's the degree of the polynomial. Okay? We only look at the exponents on the variables. This term has 1 variable. It has an exponent of 2. So its degree is 2. Okay, so I just make a note of that underneath. This one has 2 variables. What's the exponent on the x? 1. What's the exponent on the y? The sum of those would be 4. So the term degree for that term is 4. What's the exponent on the x for the 6x? It's a 1. So the degree of that term is 1. Poor little 7 out here doesn't even have a exponent or a variable. So what's its degree? 0, because it doesn't have a variable. The degree of the polynomial is the biggest one. Which is the biggest one? 4. That's the biggest one. So the degree of the polynomial is 4. Now, that really doesn't mean much to us right now, but later on, that degree is going to be important as far as when we go to solve polynomials. What does it mean? That degree tells us how many solutions we should be finding out of that when we go to solve polynomials. Not tonight. We're not solving tonight. But being able to find that degree is a basic thing that we need to kind of be aware of as we move through the material in the course. So finding that degree, we look at the exponents on the variables. Let's look at another one. Still stating the degree of the polynomial. 4x cubed minus 5x squared plus 6x to the 5th minus 8. This one's a little easier because it only has 1 variable on any term. So we're going to look at those variables, look to see if there's anybody we can put together. Are there any like terms with this problem? I got an x cubed. Is there any other x cubes? Nope. I got x squared. Is there any other x squareds? Nope. X to the 5th. Plain numbers. No like terms, okay? So that means I can go ahead and do the degree. What's the degree of the first term? Second term. What's the biggest one? 5. So the degree is 5. That's what we're after there. It's a little tougher when they throw more than 1 variable in there. This one got 2 variables in every one of them. What's the degree of this term? 7. 4.3. What's the degree of this term? 6. So 7 times so far. What's the degree of this term? What's the degree of the polynomial? 8. Easy thing. So simple, you'll mess it up. Okay? Don't mess up the degree. Degree of each term, pick the biggest. The degree of the polynomial. Okay? All right. Next thing. Name a polynomial. Okay, you name a polynomial. You want to pick cute names like, Fluffy and Mitzi, things like that. No, when you name a polynomial, there's a process to it. The process is based on the number of terms. Okay, how many terms does it have? Tells you what kind of name. And then I'm going to put an example here of that. Okay? If there's one term, the name is monomial. The prefix M-O-N-O, mono, one. Right? That's what that means. Okay? The monomial means one term. An example of that, a monomial would be 2x, one term. It doesn't have any addition or subtraction in it. Okay? Technically, just the number 2 is a monomial. We just usually call it the number 2. But if you put that x on there, then that's a monomial. Well, 2 was a monomial too because it didn't have anything going on with it. If there are 2 terms, what did you learn to ride when you were a kid, or hopefully you learned to ride when you were a kid that had 2 wheels? A bicycle, right? Bicycle means 2 wheels. So a binomial has 2 terms. X squared minus 9. That's an example of a binomial. It's got 2 terms, 2 things separated by addition or subtraction that cannot be simplified. Okay? We've always got to look to simplify before we can name it. Okay? So your x squared can't go with a 9 because we're not like 9. Okay? It's got 3 terms. What do you think the name is? Trinomial. Example of that would be something like x squared plus 7x plus 12. There's a trinomial. Trinomial, 3 terms. Anything bigger than that, 4 plus, we're just going to call a polynomial. There are prefixes for numbers bigger than 4 and bigger, but in the mathematical world, we don't do that with polynomials. Anything 4 terms or bigger, we just say it's a polynomial in general. Okay. Example of that might be like x cubed plus 5x squared minus 6x plus 36. Just a, that one's got 4 terms. It's a polynomial. So the only ones that have special names are monomials, binomials, and trinomials. The reason they do is there's some special things that we can do with those. Once it gets to 4 terms or bigger, there's not so much special things we can do anymore. There's some pretty heavy math that has to happen for that. We're going to do some of it in this class and 110 together. So we'll get there. But being able to name them is what we're after. Okay. So our job here is to simplify and name the polynomial. Okay. Example I. Let's say we had 2x to the 4th minus 3x squared plus x plus 4x to the 4th plus 7x squared minus 6x. There's just a nice couple of polynomials to deal with. We're going to simplify those before we name what kind it is. All right. Like terms, that's the name of the game. We're just simplifying, means put the like terms together. So 2x to the 4th goes with what? 4x to the 4th with addition. So 2x to the 4th plus 4x to the 4th would be we're not multiplying, we're adding. So 2 plus 4 would be 6. And then the exponents don't change when you add or subtract. Exponents don't change when you add or subtract. Exponents only change if you're multiplying or dividing. Okay. And we're not going to be doing that too much today. Actually, very little. Okay. So those are done. Next one, negative 3x squared goes with what? Positive 7x squared. So we have negative 3x squared plus positive 7x squared. That would be a positive 4x squared. Since it's positive, we're going to add. Next. Oh, minus 5x. Good job. So there we've used up every piece. How many terms does that have? 3, so it's called a trinomial with a degree of how much? How much? 4, right? Biggest one. Trinomial, it has a degree of 4. So that combines everything that we've done so far in this section. Puts it together. Okay. Let's combine everything we've done so far today. Alright. So this combines order of operations, polynomial stuff, simplifying, and then naming the polynomial. We're going to get the degree, all that stuff out of this. Okay? Alright. What's the first thing that should happen? Alright, parentheses. And can I put anything together inside of these parentheses? No. Can I put anything together inside of these? No. So parentheses didn't help us. What's next? Are there any exponents that can be evaluated? Now that's got an X on it. We don't know what X is. So nothing to do there. Same thing here. We don't know what X is, so nothing to evaluate there. After exponents is multiplication. Okay, is there any multiplication happening here? Yeah, there's this 4 in the front that's multiplying to this stuff, and then there's this minus 5 here in the front of this one that's multiplying to that stuff. So we're going to distribute 4 to this parentheses and negative 5 to that parentheses. Okay? 4 times x squared is 4x squared minus plus 28. All right. Now, whatever sign is right here in this middle, that you want to take it with you when you distribute. So we're going to distribute this as a negative 5. If that were a plus 5, we'd distribute it as a positive 5. Okay, so whatever sign is there, you want to take with you. So negative 5 times 2x squared. There you go. Negative 5 times negative 8x. Good job. Negative 5 times negative 4. There we go. Now, we look at it and say, okay, I've done the multiplication. There's not any division happening. I don't see any of that. So the next step would be to add and subtract. One, I'm going to add and subtract. I'm going to add and subtract like terms. So what goes with 4x squared? Minus 10x squared. So that would together be, yep. The plain x's would be plus how much? And then the plain numbers plus 48. That's as far as it can go. So it's a trinomial with degree 2. So there's It combines a lot of stuff we've done tonight so far. Getting close to the end, folks. All right. Okay. Last section. I'm going to use graph paper for this one, but you don't have to have it. I just use it because I'm a little bit OCD about where I put my points and stuff. As long as you get the general idea of where the ordered pair is when I draw this, you don't have to have graph paper for this. I'm just going to use that because I'm, you know, my wife says weird, but I'm okay with that. Doesn't bother me that much. All right. So we've been in the R chapter the whole time here. So if you get the textbook, it was in the R chapter for that. We're going to jump out of the R chapter and go all the way over to chapter 2 for this last section for tonight. It's chapter 2, section 1, 2.1, and it's rectangular coordinates. All right. Rectangular coordinates is a fancy way of saying the ordered pairs. Okay. Ordered pairs, x comma y. You're dealing with ordered pairs. Can't stand to not draw a straight line, so pretty straight line. There we go. Oh yeah, that's beautiful. All right, coordinate plane. This is the x-axis. This is the y-axis. X-axis goes left to right, so x values go left to right. Y-axis goes up and down. Y values go up and down. Okay, so when you look at your ordered pair, the x, the first number that's in that ordered pair, tells you where to go left or right. The second number tells you where to go up and down. I've got some students that I've had in the past, they, whatever reason, but call it dyslexia or not, I don't know, but they always swap that. They do it backwards. X, left or right, up and down. Left and right, up and down. You got to walk to the elevator before you can get in it and go up and down, right? That's that. So left and right is x-axis, y-axis is up and down. All right. Some other things about the coordinate plane. There are things called quadrants. So what it's done is it's taken the piece of paper and divided it into 4 pieces. Those are the quadrants. Quadrant 1, 2, 3, 4. Those are Roman numerals. You're not used to those. Okay. And the way they're numbered, they number them by Roman numeral. Is the standard way of doing that mathematically. Now, this is quadrant 1. It's all the ordered pairs that are up here in this part. This is quadrant 2. That's all the ordered pairs that are in this area. Quadrant 3 are all the ordered pairs that are in this area. Quadrant 4 is here. If you're on the x-axis, are you in a quadrant? No. If you're on the y-axis, are you in a quadrant? No. Okay? So you're going to have some problems on the Canvas quiz and on the test. It's going to ask you, where is this point located? And it doesn't mean put it on there. It says, what quadrant is it in? And if it's on the x-axis, then it's not in a quadrant. You would say it's on the x-axis. If it's on the y-axis, it's not in a quadrant. It's on the y-axis. Okay, so that's the difference. Now, the ordered pairs, the way they work, in the first quadrant, all the x values are positive. All the y values are positive. So if you look at an ordered pair and it's positive 2 and positive 6, you know it's in quadrant 1 because everything's positive in quadrant 1. Everything's positive in quadrant 1. Okay. Quadrant 2, you're on the other side of the y-axis, but you're still up top. So your x values become negative and your y values stay positive. So it's negative positive. So if I gave you an ordered pair, negative 6 Positive 16, you know that's somewhere in quadrant 2 because it's a negative positive. Quadrant 3, we're still over here, so the x's are still negative, but we're down here, so the y's are now negative. So it's a double negative in quadrant 3. Negative, negative. Okay. Quadrant 4, what's it going to be? Positive, negative. That. Okay. So, where, or better yet, what quadrant is the ordered pair in? That's our question. So, point A, let's say it's -3, -5. If it's double negative, where's it at? Quadrant 3. If I was going to plot that point using the coordinate plane, -3, -5, I know it's going to land down here somewhere. So I do the left to right first. -3 needs to go 3 blocks to the left from the origin. The origin is the middle point there. 0, 0 is its origin pair. 3 blocks to the left, 1, 2, 3. 5 blocks down, 1, 2, 3, 4, 5. So that I would put a dot right there and write the letter A beside it. That's how you plot a point. Easy stuff. Gotta do it right. Okay. 3, 5. There's point A. All right. Let's do another one. B. Let's say -4, 2. What quadrant would that be in? 2. And negative, positive. If I was going to plot it, I'd go 4 to the left, 2 up. Put that point there. Easy stuff. Let's do one more. 0, 3. So, want to plot that point? 0, is that positive or negative? Well, it's not on the origin. It's on an axis, isn't it? Yeah, it's 0 left to right. I'm not moving any. I'm just starting here at 0, 0, and I'm not moving to the left at all or to the right at all. But I'm moving which way? 3. So that point would be right there. Where is it located? On the y-axis. Okay, not on in a quadrant. It's on the y-axis, and it would be that point right there. Okay. If it were 3, 0, you'd be on the x-axis because you'd move to the right 3, and up and down 0. Okay, so easy stuff. All right. Next thing. Graph and equation. Next thing and last thing. Okay. Last thing we're doing. I'm going to graph a couple of equations. I'm going to show you how to use the calculator to help you, and then show you what I'm talking about here. So let's take an equation. Let's call this example B. Y equals 4x minus 1. If it hasn't been too long since you were in a math class, you might remember how to graph that a different way. But it's been a while. You may not remember how to graph that at all. What I want to show you is that you can graph this using ordered pairs by just picking some x values, okay, and plugging them in and working them out and evaluating that expression, just like we've done in the sections earlier. Okay, if I take and make a table, so let's do that. Gotta have a straight line. I'm going to pick some x values, and I'm going to get the y value from them. Okay? I'm going to pick easy ones, like -2, -1, 0, 1, and 2. If I pick those x values, it's going to mean I don't have to draw a very big graph. I'm not going to get very far out there. And those numbers are pretty small, right? So I can makes the math a little easier on myself. So I'm picking x values that are easy, okay? What I'm going to do is I'm going to plug them in for x in that problem. 4 times negative 2 minus 1. And then I'm going to do order of operations to work it out. 4 times negative 2, that's multiplication. That happens before subtraction. So I'm just going to multiply 4 times negative 2. That'd be negative 8, right? Negative 8 minus 1. That's negative 9. So I get negative 9 that goes right there in that table. What that creates is it creates an ordered pair. Negative 2, negative 9. Where's that at on the coordinate plane? What quadrant is that in? 3, double negative. Double negative is quadrant 3. Okay? I'm going to go to do the same thing for the x being negative 1. What's 4 times negative 1? It's negative 4. What's negative 4 minus 1? Negative 5. Then I'm going to go plug 0 in. That one's getting easier. 0 times 4 is 0. 0 minus 1, negative 1. So I got a negative 1 right there. I get to the positive numbers. They're even easier now. So 4 times 1 minus 1, that's 3. 4 times 2 minus 1, 8 minus 1 is 7. That math I can do. Okay? What I've got now is I've got 5 ordered pairs. Do I need 5? Not every time, but 5 is a good number to have. Because usually, if the graph is going to curve or do something weird like that, within those 5 numbers, you'll start seeing that. Okay? This one, I know it's going to make a straight line when I graph it. I'm going to show you. But the next one we do is going to do something like that. And so having those 5 numbers is helpful out of that. So I'm going to draw a coordinate plane. And I'm going to plot these numbers. So I got to make sure I go all the way up to 7 and down to negative 9 with my y-axis. I think I got room there. So I'm going to plot those points. I'm going to go to negative 2, 1, 2, negative 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's negative 9 right there. Okay. I'm going to go all the way up to negative 2, 2, 4, 6, 8, 9. Right there. There's the first dot. Go to the next dot. Negative 1, negative 5. 1, 2, 3, 4, 5. 0, negative 1. 1, 3. Over 1, up 3. Over 2, up 7. 3, 4, 5, 6, 7. Pow. Da, 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 da. And I'm going to connect all those with a line because they make a straight line. If it were curved, I'd try to kind of make a little sweeping curve through there. Here's the beautiful thing about the graphing calculator. If you've got a graphing calculator that you've got an equation that's got y equals, it's got a button that says y equals on it. I'm going to press it. I got some stuff I did in college algebra in there. I'm going to get rid of that. All right? I just cleared those out. Y equals, and then I'm going to type in the equation that they gave me, which was 4x minus 1. So I'm going to hit 4, and then to get the x, it's right beside the alpha button there. And then minus 1. Watch what happens when I hit graph. That is sweet. You get the picture of the graph you're trying to get, okay? Another sweet thing about that is I can hit this trace button and then type in any of those x values that I plugged in. Try negative 2, negative 2. Look what it got me for the line. If I type in negative 1. Boom. -5. I didn't do another negative. It's 0. Boom. There's -1. +1. Boom. +2. Boom. Same y values that I found by hand. I'm verifying it with my calculator. Okay? And I'm verifying there, not just doing it with the calculator. You know that's handy. Try to do some stuff without the calculator as much as you can, but I'm showing you ways to check and make sure you're doing things right. That's what I want out of it, okay? So again, you're hitting y equals, you're typing in the equation, 4, the x is right beside alpha, -1, hit graph, it draws the picture, and then to check your x values, you hit trace and then type in the x values you want to check, okay? You can always, I remember I videoed this so you guys can go back and rewatch that once you get your graphing calculator, so you'll be able to do that. I'll send the link to that this week. Probably tomorrow, but it'll get done. All right.
When you start in the
Mm-hmm.
do you always start with -2, or how do you know how to range it?
I generally do start with -2, and if I see something weird happening, I might change that or add 1 to the end or something. Just if I see a weird curve starting to happen when I start plotting on them, I won't really know that until I start plotting on there. So a lot of times I'll make my table, and as I'm making it, I'll just go ahead and plot that point as I find each one and go from there. So it kind of just, you get the feel of it after you've done several of them. Usually, if the x doesn't have any exponents, then it's going to be a straight line. So you really don't have to worry about it too much. You just go ahead and run right through with it. But if you got one like this next example, last example tonight, we're almost done, guys. Just hang with me. I know you're tired. I'm pretty exhausted too. So here's one to finish on. This one, it has the squared on the x. So this is one that would kind of raise your eyebrows and be like, there's something weird going on with this one. It's going to be a little bit different because it's got an exponent on the variable. Okay. Same idea though. We're going to build a table. I'm going to pick -2, -1, 0, 1, and 2. Just as default, I'm going to start with those. Okay? If I plug those in and work them out. -2 squared -4. What's -2 squared? It's 4. 4 minus 4, 0. All right, that's nice. What if maybe I should go ahead and plot those as I'm going. Kind of like what I was giving you advice to do. Just follow my own advice. Not do as I do, not as I say. All right, so -2, 0. That's right there. And I'm going to plug in -1. -1 squared is 1. 1 minus 4 is -3. So -1, -3. That's that point right there. And plug in a 0. 0 squared is 0. 0 minus 4, -4. That's that point right there. Plug in a 1. 1 squared, 1. 1 minus 4, -3. Oh, yeah, that's the weird thing there. Then I start to repeat numbers. 1, go to the right 1, down 3. That's where I got the 1, -3. And then when I plug in 2 squared is 4. 4 minus 4, 0. It repeated again. Okay, so I get this symmetric graph is what's going on here. If I picked another x value to the left here, like -3, -3 squared is 9. 9 minus 4 is 5. So I would have this point up here at 5. It's just making a big. It's like a big U. Is what kind of shape it makes. It looks something like that. If I go to my graphing calculator to kind of verify that that's the shape that I'm getting, go to y equals. I'm just going to hit clear to get rid of the equation I already had in there, and I'm going to retype this new one. I need an x, so remember that's right beside the green alpha button. So I'm hitting x. I need to square it There's a button for squaring. It's right above log. And then -4. Okay, so I hit y equals to get here. X squared -4. And then I hit graph. That looks like the picture I'm getting. Okay. And then again, I can check my X values by hitting trace and then just typing them in and hitting enter. And we get those. And if you wanted more, if you wanted to add more X values, you could. It's not a requirement, but it is good to do. Okay. Okay. So that finishes up our material for tonight. Some suggested problems from each section. R1 in the 11th edition, it's page 6. It may be the very same page numbers in the 12th edition. I'm not sure. Miss Cindy, you may want to help us out here with that, because my numbers are from the 11th edition and I haven't received my 12th edition yet. R1, where do the problems start? I've got it. The exercises. Page 6, so it is the same page on that section. All right, good. Page 17 for R2. And guys, these are suggested problems that you would look at. If you do 3 of them out of each little subsection and you got it, then there's no need to do all of them at all. I don't want or expect you to do all 91 through 93 odd. I mean, that's, you know, that'd be crazy. I would try to look at that, and that'll just help you so that when to the Canvas homework part, you're not just going in there blind, not knowing what kind of problems you're going to get. The problems that are coming out of the book are similar to what you're going to see on the Canvas thing. The only difference is the Canvas thing, most of those are going to be like a multiple choice type scenario. Okay, so the problems out of the textbook are kind of a prep for that Canvas, and the Canvas is kind of a prep for the test. The labs we will do next week will cover these 4 sections, and we'll go through that material. Again, we'll come in at 5:45, normal class time. We'll do labs first, and then I will cut off labs at a certain time, and just so, and then we'll do lecture after that. So next time we meet will be September the 10th. Next Monday is Labor Day. You got the weekend off. So you got 2 weeks for your first Canvas homework assignment to do. Email me if you got questions, or you need, and if the disability statement applies to you, make sure you call them, get that ball rolling, so that by the time we got our first test coming up, I'm doing what I'm supposed to be doing, and you're getting what you're supposed to be getting. So email me if you got questions. That's the best way. I'll get back to you as soon as possible. Look forward to the semester. Let me get names one more time before you go, so I can try to do this. Joe. Oh, Lord, I'm going to screw this up. Christy. Havana. I'm going to screw up your name. Rhiannon. Rhiannon. Okay. And then Kristen. Dylan. William. Justin. Miss Cindy. Crystal. Samantha. Oh, getting down to the bottom, I screwed up every time. Teresa. That's you. I'm going to know it the next time with me. Okay. And then Carly. Is you. Victoria. All right. I'll try, guys. I'm doing my best. All right. Appreciate it. Y'all have a great week. Enjoy your time off next week, and I'll see you September the 10th. Okay. Whew.